So I'm the director of engineering for mobile at LinkedIn. So my role is to build all of the apps for phones and tablets on the client side as well as on the server side for LinkedIn. So everything that's on mobile is built by my team, and that's kind of my role. I want to just kind of get a quick idea of types of people in the audience. How many people here are product managers? A couple. How many are designers? Okay. And how many are developers? Oh, that's good. Okay. Okay. It's a pretty good ratio. So generally what I'm going to try to do is walk through how we build mobile applications and utilize both Node.js and HTML5 to do that at LinkedIn. It's kind of an interesting question because I think both the term Node.js and the term HTML5 are really generic. Like, people have just stuffed all sorts of technologies under those words. So I'm going to try to go into a little more detail on what that actually means for us, like which libraries we're using and what we're doing there. So let's get started. So you guys should be, anybody who's building products in general are probably pretty familiar with these 4 stages of building. So we have the design. This is product design, UI design, technical design. Then you usually go into code, you have some testing, and you have some deploy, and you do this many, 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 many times. Hopefully at some point you have a product that pops out. So typically, for most products, this is your typical cycle. The one sort of difference on mobile is that you kind of are doing this across a number of platforms. The way we break our platforms down is iOS, Android, the browser we look at as a platform, and then currently the other sort of devices, BlackBerry, Nokia, Windows Phone 7, Samsung, that type of stuff. So let's start off with design. I'm going to kind of go through this fast. You guys stop me at any point if you want to, if you want me to slow down, but I'm going to go through the product design stuff a little bit faster because it's a smaller audience for that. So whenever we start by designing our applications, we really try to separate interaction versus visual design. And so usually when I say this, a lot of people, it's difficult to understand what the separation is. So I've tried to sort of build a metaphor that I'll use throughout the presentation, and it'll help sort of separate when I'm talking about interaction, when I'm talking about visual. So think about interaction design as building a floor plan for a house. You're defining what each of the rooms are. You're defining how you can get from one room to another. That's your hallways. So for example, you have a living room. You know what you're going to do in the living room. You can sit, you can watch TV, that type of stuff. You know what you're going to do in a kitchen. You know what you're going to do in a bathroom. You generally do not have your toilet in your living room. So you really want to sort of define rooms that are for a specific purpose, and then you want to have sort of doors and hallways that take you between them. So we try to stay away from the visual part, the paint, the furniture, the carpet, what interior designers do in sort of the house metaphor. And then for each room, and so if you haven't already figured it out, each one of our rooms is a screen in our world, in our app. Has and does for each screen. So what does each screen have on it? And then what can you do from each screen? This is where we start off with our initial design. And then we build for pretty much all the platforms in black and white first. We do this on purpose so that when we're doing user testing, people have visceral reactions to color. So sometimes they're so focused on, like, oh, I don't like that it's red or blue or green or whatever, or the shading's not right. So we really focus on a black and white sort of UI design before we kick into full development. So if you look at the current mobile applications, these are our 4 rooms. We have the stream, view, inbox, and following. And we have a few hallways, search, compose, and notifications. The breadth below 4 and the depth below 3. So you generally only want to have about 4 rooms on mobile. If you try to get more than 4 rooms, people generally are lost. They can't get to the 5th room, or they just don't know how to get back. and your depth is less than 3. So when you're in a room, you tap on something, you go screen in or another screen in. You really don't want to go more than 3 levels deep. Once again, people will get lost. They don't know how to get back out, and they'll sort of lose sight. So what about the differences between the platforms? There's a few differences. They're actually not that hard to separate. On-screen back versus hardware back. There's a concept of using back versus up between iOS and Android, where your refresh is and where your settings are. And then we really use visual design to kind of separate the user experiences. What do the buttons actually look like? What does the paint look like? That type of stuff. But at the interaction level, at the room floor plan layout level, we do not have that much separation. Another thing people usually ask me is, why do you guys have a mobile web solution? Why not just have an app? Why do you really need it? And this is sort of the answer to that. So typically, when you're looking at any sort of web-based property, internet property, you have these sources of traffic. You have SEO, search engine optimization. You have email. So if you send out email and they click on it, it comes back. And you have organic. Somebody typed in your domain name. On mobile, that would be like finding your app and launching it manually. So for LinkedIn, at least, a huge chunk of our traffic comes from email clicks and email links. And that takes you into the mobile web. So for actually a lot of mobile applications, this is a prime way to sort of initially seed your application and get people to sort of use it. So let's go into code. I know I flew through that. Any questions on that area? Like, should I just keep going? Keep going. All right. This is the basic structure of our design or our architecture for our applications. So I'll explain what the percentages are in a second. We have the 4 major platforms, or the way we look at platforms. We have iOS native, Android, mobile web, and then we have other OSs, our wrappers around our mobile web solution. We have this sort of framework that we use internally. It's a mobile web JavaScript HTML framework. I'll talk a little bit more detail about what that is. What is that HTML5 framework we use on mobile? All of these applications are some part built on top of this mobile web framework. So here, it's 70% of it's actually built in HTML and JavaScript, and only about 30% is native code. 80% on Android is native, and only about 20% is JavaScript and HTML, mostly because of some of the performance constraints we have on Android with the browser. And mobile web, of course, is 100%. It's the web. And then other OSs are 100% from our standpoint, because we usually have just very, very simple wrappers. We then communicate over something we call screen-based REST APIs. I'll talk a little bit about what that is in the coming slides. Which then talks to our mobile server. So our mobile server is made up of Node.js and MongoDB. I'll go into a super amount of detail. This is sort of give you a vocabulary on what the mobile server is and how Node.js works. And then we have this domain REST API that talks to the LinkedIn platform. So one thing that people are surprised by is whenever I say LinkedIn platform, they're like, oh, you guys have all these custom APIs that you are using to talk to backend LinkedIn. All of the mobile solutions today are built on top of literally the public LinkedIn platform, the one that you can get to on developer.linkedin.com. So all the functionality that you see on all of our mobile apps is built on top of this API. So let's start going into some detail. We'll start off with the mobile server, the Node.js and MongoDB. So before I kind of go into why Node.js, I kind of need to walk through a little bit of change that's happening with HTML5 as a result of HTML5 and the way we're sort of building these client-side applications. So I'm sure most of you are familiar with classical model view controller or variations thereof. Is that true? Everybody who knows model view controller, can I have a hand raise? All right. OK. So typically, if you guys have built Rails-based systems like Ruby on Rails or Django and Python, or if you've used JSPs in Java or any system at all for web-based applications, you'll have a controller. You'll have some sort of templating language, ERB, JSP, something like that. And then you'll have an ORM layer or something to store stuff. Maybe you have, like, if you're using MongoDB, even there's stuff like Active Record, Hibernate for the Java, pylons, that type of stuff. And every time there's a request that comes from the client, generally a process is spawned, or a thread. Process or thread, I'm using them interchangeably, but they're spawned. And that socket is held open until you're done doing your processing, and then it responds. Usually there's one processor thread per request, and then you have sort of a queue of sockets that are sort of waiting to be processed. So as you go into tiered systems, as you start to grow as a company organization, I'm sure you guys have this. You've separated your data service into a separate process, and you moved your controllers and templating forward. As you continue to grow, the number of data services you have grows, right? Because the domain models that you have. So for us on LinkedIn, like profile is a data service. Our network updates is another different data service. Our inbox messages, that type of stuff, is another data service. So they're separated by the type of data they are. And then I do want to make a point on the last two there, tracking and a background queue. So usually in these models, when you're processing this way, you don't want to sort of block the response to the user, right? So when a request comes in, you don't want to block the process. So what people typically do is they stick something in a background queue, and they respond. And then they either poll again or something like that to effectively check if the processing's done. So one of the big differences that's changing when you go into HTML5 is look where the dotted line is moving. So the dotted line, the client-server border, is above all this stuff, right? The server rendered. In HTML5-based applications, the client-server border has moved. It's moved down here to this dotted line. So now, this client side, this is running in the browser or in an app, whether it's native code, whether it's JavaScript code, it's sort of running down here. It needs to talk to all these backends. And you're like, well, OK, how's it going to do that? You really don't want to sort of have one connection talking to every single process here. And you sort of lost the value of the background queue, right? Because there's nothing sitting there to sort of help you with that. So this is where Node.js comes in. This is really what Node.js, at least we believe, is really good for. If you've moved, in a classic MVC model, what we've done is we've moved the views and the controllers up here into the browser. You've moved the models back here. So you say, well, what's left? A very thin layer. That's all it's really doing is some aggregating and some formatting. And another thing you'll notice is that the background queue I've kind of graded out. It's gone down in necessity because Node.js is evented, and I'll talk a little bit about what that means. Because Node.js is evented, you're not as dependent on sort of giving up a process, giving up a thread, or giving up responding immediately and then not being able to wait for something to complete. So why Node.js? The two main reasons is that it's evented and it's JavaScript. And I'll explain. So for our use case, and I think a lot of people will have this use case as you build more client-based applications, HTML5-based or mobile, is that most of the front end, the thing where Node.js was sitting at, most of what it's doing is just sitting there waiting for other things to do stuff. It's I/O bound. It's sending requests to backend service to actually do some processing. It's talking to a database that's actually trying to read off disk. But effectively, it's I/O bound. It's not really doing that much. All it's doing is some string manipulation. So it's manipulating strings, the front end. It's sort of like a typical example that most people do is, oh, I have a user object that's stored in my database somehow. I'm going to get it. The user object has a first name and a last name, but you want it to show up as name in the UI, so you concatenate them, right? First name plus last name. Typical model. I feel like I see that replicated in every piece of code everywhere. So manipulation is strings. So for the evented part, the I/O bound, because it's I/O bound, the evented part is really, really important. Because it's mostly string manipulation, the JavaScript part is actually important. JavaScript, at its core, when it was built to run in the browser. And for the number one thing you kind of do in the browser is you do DOM manipulation and you do string manipulation. So The V8 virtual machine, which is what Node runs on top of, is actually optimized for string manipulation. So if you look at things like the Java VM, the Python VM, the Ruby VM, they have a little bit, they're not tuned for this case as much. It's not that they can't handle it, but they're just not tuned. The third thing is lots of persistent socket connections. So this is really a mobile case that we take advantage of. Is on mobile, I know that all the advertising is talking about more and more bandwidth, right? 3G, 4G, faster, faster. The biggest issue on mobile is actually not bandwidth. The biggest issue on mobile is latency. It is the amount of seconds it takes for you to actually step. And you hear I said seconds. It's not milliseconds, but literally seconds. It takes you to sort of establish a net connection. Means that you really want to limit the number of times you're making HTTP connections up to your server. You want to kind of create one HTTP connection and then try to send a lot of data back and forth on it. So the concept of sort of comet-based connections or long polling connections, that type of stuff, has been around for a long time. But in the process-based model that we talked about before, that means I would have to have a dedicated processor thread tied up holding that socket open. And that actually causes some big problems because eventually as you start to scale up, that means every one of your users is taking up a thread. And at LinkedIn scale, when you have millions of users, you have millions of threads, it starts to cost money. So we try to keep the socket open. So we establish one connection up, and we try to keep that socket connection open and communicate over that connection, which actually gives us about a 20 to 30% boost in performance. Another huge benefit is that client developers are actually doing server development. So one of the other issues that I always hear about Node.js, how many of you have actually used Node.js? Okay, so I'll go into a little more detail here. So there are a few major complaints about Node.js. One, actually, both of them are that it's evented and it's JavaScript. So the two things I really like about it are usually the two biggest complaints about it. The evented part of it actually causes you to change the way you're going to program. A lot of server-side developers are very used to a model of, if I want to do something, I spawn up a thread, I do that in the background, and then I sort of continue. Moving to an evented model really requires you to have this concept of sort of responding to events, responding to actions, responding to something happening. And surprisingly enough, client developers are naturally attuned for that because every UI framework, whether it's native or in the browser, is evented by definition. Forget about the language. It is evented by definition, right? You are waiting for somebody to click on a button, and then you will respond to it. So for client developers, it's actually been easier for them than doing the threaded model and trying to figure out synchronization blocks and all of those aspects. The second half of it is the JavaScript side of it. So JavaScript it is more recently starting to become a language that people are embracing. But in the past, a lot of people were worried about, well, it's going to turn into spaghetti. It's hard to understand the code base, that type of stuff. If you look in the Node.js community now, there's some libraries that you guys should definitely look at, like Step or Async, which provide you a little bit of structure on how to organize your JavaScript in a way that makes it a little bit less of a chance to go to spaghetti. It's still always dependent on the engineer. You can write spaghetti in any language. JavaScript definitely does make it harder or easier to write spaghetti, and so there's some good design patterns. By looking at those things, you'll kind of get an idea of how to write your code in a way where you don't end up with sort of a sequence set of callbacks. The last big sort of benefit is that it's evented all the way down. So what does that mean? So there are evented frameworks in other languages. So there's Event Machine in Ruby, Twisted Python in Python. There's the Play framework in Java/Scala that's NIO based. So our biggest concern, and the reason we ended up going with Node.js for all of those, is that the way an evented model works is that every time you do any communication, anytime you do anything I/O to something else, you have to make sure that that thing is asynchronous as well, right? Because if it blocks, it's just like in your UI for all the front-end developers. Like if you do something that's going to block the UI, then it's just going to it's going to feel like the UI is blocked. It's the same thing on an evented system on the server. If you block that main thread, you're blocking all requests for the entire server, which is really bad. And in most other systems, in most other languages, the libraries, the benefit of all the libraries that are currently there, all the Java libraries, all the Python libraries, all the Ruby libraries, is that they're all synchronous, right? In fact, we put out Java libraries to talk to the LinkedIn platform. They're synchronous. We put out Ruby libraries. They're synchronous. There are asynchronous versions of these things, but it's definitely, you have to make sure every time you include a new third-party library or something from the internet that they've written it in an asynchronous way. And on Node.js, because it's sort of a relatively new, I mean, it's not really all that new anymore. It's 2.5, 3 years old. It's relatively new. It's come up with the assumption that everything has to be evented. So a lot of its library sets, a lot of its modules are evented all the way down. They're evented by definition. And so that just gives us a little bit more flexibility in terms of choosing our external libraries, third-party libraries that we use. Do you guys have questions? Because I went through a lot of data in this slide. Yeah, so we definitely did perf analysis on just plain JavaScript execution for like loops and stuff like that. So JavaScript is, the V8 engine at least for the test cases we ran, is slower. It's like 10% slower. But I'm not sure it really, we're not CPU bound. We're IO bound. So as a result, it wasn't really a big issue for us. No, so that's the, so his question, let me repeat the question. The question is like, oh, you're going to hold these millions of sockets open for the persistent socket connections. That's obviously a process or a thread per socket. How could you possibly be doing that? That's the whole point of the evented model for Node.js, is that Node.js is literally a single process. There are no threads. There are no sub-processes. There's nothing. It is a single process. Every time a connection comes in, it's like it literally just holds the socket connection. It's not associated with the process or thread or anything. Holds the socket connection. It has a queue of sockets. And every time something comes in on one of those sockets, it lets you process that data, and then it goes back and looks at what's in the queue again. There are no threads. There are no multiple threads. So how do we scale to millions is, each process can handle X, literally like, I don't know, X 100,000 connections. And that's how we can sort of scale that model. Yeah, I can share some stuff. I can't obviously give you guys exact details. So generally our Node instances, so if you're just doing like you send a request up to Node and it sends you back OK, this is like the typical thing that I see in a lot of these like bandwidth tests. It shows that, oh, a single Node instance with a single process on a single core running in about, I think like 30 meg of RAM can handle somewhere around like 150,000 QPS. It's like crazy. But that's not reality. As soon as you start writing JavaScript in and it starts to actually do things like actually concatenate strings and that type of stuff, what we have been able to reach for our code base is around 160 to 200 QPS per node instance, per node process, running in about 30 to 40 meg of RAM. So obviously, the more JavaScript processing we do, that number goes down a little bit. But overall, that's pretty high. That's higher than most other systems can do on a per process level, as well as in terms of memory utilization. 30 to 40 meg for a process is pretty low on some of these backend systems. And then we usually lock each node process to a single core, and that's how we get scale on a multi-core system. You can actually tell Linux, if you're using Linux or Solaris or whatever, to lock each process to a specific core, and that gives you an optimal distribution model. Other questions? So his question was, are we using Socket.io? We are using Socket.io. Yes. Let's talk a little bit about our node our mobile server and what are the components in it and what do we use it for. So obviously we have a load balancer in the front. We have Nginx. Nginx we use as a web server. To be honest, I think within the next month we're probably going to remove Nginx and just have load balancer going straight to Node.js. Originally, we put in Nginx because we were concerned because Node.js is relatively new and we wanted something a little more stable. The reason we chose Nginx over Apache is Nginx is also evented. If you put a process-based system in front of an evented model, you have lost all the benefits of your evented model because now you just have a different layer with all of the processes and threads in front of you between you and the client. So Nginx is an evented C++ based web server that is super popular, super efficient. Now that we're actually a little bit further along, especially since we've moved all of our static content to CDN, the web server is really not providing that much value. And so, for example, on the mobile server side, we still have Nginx in front. On the new tablet application and the tablet server we just launched, we don't have Nginx in front anymore. It's just straight load balancer to Node.js, and that's it. So Node.js servers then talk down to a few different things. MongoDB. So we don't actually use MongoDB for a ton. We use it to store our authentication keys, effectively cookies to look up a user. But all of the real data is stored behind the LinkedIn platform. And that data, a lot of that data is stored in a variety of databases. We use MySQL, we use Oracle, we use React, we use Voldemort. So it's a variety of databases, and it just depends on the use case that we need to use for it. For us, one of the issues we've definitely run into is with MongoDB. From an operability standpoint, MongoDB is has been the hardest thing that we've had trouble with from an operability standpoint. And then we have a logging server. Logging server is really simple. I really recommend sort of trying to build some simplistic logging server. A lot of people sort of dump all of their logs, but they don't actually have something that can grep it and analyze it. There's definitely public tools out there that are things like Splunk, which costs money, or Loggly, which costs money, but you can also write a simple one. All it does is build an index, a text index into it, and that allows you to do some simple histograms, so you can do grep across all of your logs. And I know that sounds not very useful, but once you have the system, it gives you huge benefit to be able to see real-time what's happening. You can kind of get a simple, easy distribution of like how many errors and what types are they happening without having to write a bunch of Perl scripts, that type of stuff. And then we have a tracking server. A tracking server, we actually have two types of tracking that we do. We obviously do tracking into our data warehouse to keep track of large sets of actions and page views, that type of stuff, completely not attached to a user. But the other thing we do is we have this thing called in-graphs. Super important for us to measure operability. It's a counter-based system. So for example, every time we make a request to retrieve a profile, we increment a counter that says profile call counter. The reason we do this on the Node.js side, the counter is actually incrementing, and we're calling the tracking server saying, hey, increment 1, increment 1, increment 1. The reason we're doing this is trying to parse all of that information out of the logs after is actually really CPU intensive, and it takes a long time. But if you're calculating it up front, it's really easy. So what we have is we have these charts that kind of show us, hey, you're making 150 calls a second to profile. And then we have charts that show us that information week over week. So we can always see when we launch a new feature, hey, suddenly did profile calls drop? Did we break something? Or we launched a new feature, profile calls went up through the roof. Did we do something? So it's a simple example, but we use that not only for operational metrics like QPS in or like number of MongoDB hits, gets, failures, that type of stuff, but we actually also use it completely for our product metrics. So we real-time measure like how many people are viewing the home screen, how many people are viewing the use screen, how many people are sending invitations, how many invitations are sent. And we sort of track all of that data real time so we can get week over week trending. I think I covered most of this stuff. Login track. The platform transport, yeah, JSON in, JSON out. So generally, all of this stuff communicates through, this is obviously not HTTP based. This one goes over syslog. And this one is HTTP based. And then we have the LinkedIn platform, which is also HTTP based. All of them generally have JSON in, JSON out. So JSON is coming the request comes in from the client. We make requests out to the LinkedIn platform and all these different things, convert to JSON, and we send JSON out. So from a Node.js and mobile server standpoint, everything coming into mobile servers, HTTP JSON, and everything going out is HTTP JSON. So some of the benefits of MongoDB is that it actually, because it's an object store, plus it allows you to have this query language that sort of like lets you query inside objects instead of sort of using the SQL style model. We aren't really taking advantage of those aspects. We're kind of using it as just like a blob-based storage, like we have a key and a value, pretty much a key value store. And we're just having issues with, as it sort of scales up, as the number of requests go up, that type of stuff, it tends to continually eat memory. And maybe that's just a tuning problem that we don't understand yet. But I think we're having trouble from people who understand how to operate it very easily. So for the use cases we have, I'm not sure we're getting the value versus the pain that we have for it. Replica sets is another problem on MongoDB. Replica sets is a concept of you can have multiple replicas, and it does automatic rebalancing whenever one goes down. So we have a 5 replica set. If one goes down, it'll revote another one as the primary. One of the issues with this model is it takes almost 2 minutes for it to pick a new primary during the replica set sort of downtime. That means that takes our access to all our authentication out for about 2 minutes, which is not good. So I'm sure these are solvable problems, and maybe we don't have the skill set yet, but we are definitely struggling with it a little bit. The only thing we're storing there is auth token. So the standard API has a OAuth-based token model, so it's a consumer key and token. And so when you authenticate, you have to store a token and a secret. That's where we store the token and secret there. That's it. Somebody else had a question up there? How do we handle the security of what? So we run over, we actually run it over HTTPS, and the HTTPS actually terminates at the load balancer level. So we don't do, pretty much it's all HTTP inside, but up to that point, it's HTTPS. So we have secure transfer of data. If you're asking for like storage security, oh yeah, so yeah, cross-site scripting. So generally in Node.js, we don't do evals. So if you don't do evals, you're generally okay. We don't do that. We do JSON parses, but JSON parses literally are looking for structured JSON and not going to execute code at all. In terms of on the client side, we have a security team who does security analysis and audits of all of our JavaScript code, we run sort of tests against it to see if we have cross-site scripting attacks and that type of stuff. There are other questions? Okay. So I talked a little bit about screen-based JSON. Screen-based JSON was the way that the clients, now the HTML5 and native clients, communicate with the mobile server. So what does that JSON block actually look like, and what is a screen-based JSON versus like anything else? So in general, so that we can sort of limit the number of round trips, we say, okay, every request, it's a single request per screen. So every screen has a single request. We make the request up, and we get a JSON template back. And the JSON template we get back is something like this. We have nut1, a time, a header that says, wow, this is pretty cool, a footer that says shared by Kiran Prasad. So if you look at one of the NUS items or the network updates items on the LinkedIn's main screen, this tells the client how to render it. So the natural question I get is, well, why don't you just send HTML back? Because then it'll know how to render it. The problem is if it's a native app, I can't render the HTML. So I need sort of like a simple pseudo language that just says, so like, okay, when you see a nut1 and you see a header, okay, make sure it's bold, it's in the upper left-hand corner, these pixel coordinates, that type of stuff. And so we have an agreed interface between the client and the server that says this is how you will lay stuff out. It's not as expressive as HTML and CSS can be. In fact, we're trying not to make it as expressive as HTML and CSS, so we don't reinvent that and have to build another rendering engine in native code. But the benefit we get of this is that now it's updatable on the server. We want to define a new sort of another version of a nut type, or we want to suddenly, instead of showing a network update, we want to show inbox message in your NUS stream. We just have to sort of transform it into this thing, and that's what the Node.js layer is doing. We just transforms the backend data into this model, and the UI will render it. This really gives us a ton of flexibility on the mobile side, because that means on a per screen basis, we can decide whether we want to build that screen in native code or whether we want to build that screen in JavaScript and HTML, and it really doesn't have a significant impact on our backend servers, and it gives us the flexibility on the client side to get performance. The question is there impact on SEO for loading JSON-based data? Yes. So this model is designed around a concept that you're building applications. And so you're right. So if you have an index file or scraper file that you've set up that you want, like Google to scrape or something, what we have done is we've actually just built since this is JavaScript and it's JSON coming out, we actually just use a simple template that dumps all of the content and points the robot.txt file at that. So it's not a viewable file, but it's a file that a crawler can scrape. And that gives us the ability to do SEO management that way. We also have the desktop site, which gives us a huge benefit, is that we also let them scrape that. So we talked a lot about the server. I'm going to go more into the client-side components now. I'm going to start off with the iOS side and talk a little bit about that. So the natural question is, like, what's native? I told you, 30% is native and about 70% is web-based, and we're actually probably moving more web. So I'd say like maybe even 80 to 85% is web now. So it's native for all infinite lists. So what's an infinite list? So our network update stream is actually an infinite list. You scroll, it keeps loading more. And it keeps loading more as you scroll. That's effectively what we call an infinite list. We have tried, so before I was at LinkedIn, I used to run the platform and applications team at WebOS. WebOS was a fully JavaScript and HTML-based OS. It is really, really hard to build an infinite scrolling list in JavaScript. I have still yet to see one that is built that is performant. Not just scrolling, but scrolling a list while you're adding new elements to the bottom of the DOM and taking elements out of the top of the DOM and not having a glitchy scroll performance as a result. If any of you guys can solve it, come see me. I would love that. But that's definitely one of the places where we stay native. We also stay native for the window manager. So when you tap on the LinkedIn, it sort of goes into this mode where the four layers are there and sort of like zooms them down and kind of does a little cutesy bounce and stuff. To get that to happen in JavaScript and HTML, it just really wasn't possible. It wasn't performant. Not necessarily it wasn't possible. We got it to happen. It just wasn't performant. But for all of the other screens that are not these cases, we've actually gone more and more web. So actually, this is a web-based screen. This is a native screen. This is a web-based screen. This is a web-based screen. We generally try to make choices on a screen-by-screen or action-by-action basis. So Android, native. So here we went native with most screens. The reason we went native with most screens is that the Android browser, at least before 2.3, doesn't support CSS3 based, hardware accelerated CSS3 optimizations that iOS does. As a result, a lot of the simple transitions we wanted to do, a lot of the layouts and scrolling we wanted to do just really wasn't possible to be done in a performant way. We definitely focused at LinkedIn on speed. That's sort of our mantra, is we build simple things. Simple is fast, easy, reliable, fast being the most important thing. And we could not figure out how to make it fast. So a lot of the screens are actually native-based. And we use web views for about 20% of the screen. So this is a web-based view. This is a native screen, just to give you an idea. We're definitely moving more towards HTML5 as the penetration of 2.3 and above devices happen. We're moving more and more to HTML5, so it's probably not even 20% of screens anymore. It's probably like 30 or 35. But We did go more native. So the question was, what specifically made you go more native and less browser on Android? And so the reason we went more native, really the main reason we went more native is that the browser is just less capable in terms of performance. The JavaScript performance is slower, significantly slower than iOS for us. The CSS3 hardware accelerated animations don't exist on earlier versions of Android. I think it's 2.3.2 and less or something. And so the browser just isn't as capable. And if you look at the set of devices that are out there based on our demographic of users, that actually makes it really tough to have a performant system on Android. Does that answer the question? No, yeah, so it's a great question. What about Chrome on Android? So Google released a Chrome browser for mobile recently. I think it was like 3-4 months ago. The Chrome browser for mobile is awesome. It's phenomenally good. It is just not the default browser. And the number of people that are going to download a non-default browser on an Android device is too small for us. And so I think as the Chrome browser becomes the default browser on Android, I think there is a huge value proposition for us. We will double down heavily. The Chrome browser is actually phenomenal for us right now. Mobile web. So I told you we have this sort of mobile web framework that we use across all our applications. So what is it? What is it based out of? What's the magic? There is no magic. We're using all open source components to actually build most of our UI. We use Backbone for MVC. So now that you've moved the view and the controllers down into the client side, you need a typical MVC style model that you would have had on the server side on the client side. We use Backbone. Backbone.js is the library we use for that. We use Underscore. Underscore provides a bunch of utilities that you're really used to in most other languages, like collections classes in Java, list manipulations in Python and Ruby, that type of stuff. It also provides us templating. So you can sort of have a template. So like in JSP land, you normally have a template, and then you write sort of JSP script-ish stuff in there. In ERBs, you use Ruby. So in Underscore's template, the templating language is JavaScript. So you see that theme we're keeping with JavaScript now from all the way through on the templating side, on the controller side, as well as on the backend side. So it gives you a lot of flexibility in terms of your developers. Zepto is something we use for DOM manipulation. We use this instead of jQuery, mostly because it's built for mobile. I think gzipped and compressed, it's somewhere around 4 kilobytes, which is like super small compared to jQuery at the same stage. And we use iScroll for scrolling for the cases where fixed position elements, like on iOS 5, fixed position elements were available, but before that they weren't, and on Android they aren't. So we use iScroll for scrolling. We use the local storage for a personal cache and a hash-based loader. I'll talk about what that means. So mobile browsers, the caches are not very friendly. They pretty much kick you out whenever they feel like they are low on cache. So we are using local storage as a personal cache. That means we do cache management in it. So that means we actually store all our JavaScript files in your local storage. All our CSS files are in local storage. Our photos, our pictures are in local storage. We base64 encode them, send them down as text, and we store them. And so we literally just store everything in local storage. And local storage also has a limit. I think it's a 5 meg limit by default. We're way, way, way under the 5 meg limit. The way we then sort of figure out, well, how do you get a new version of the application, of the JavaScript? Let's say you made a change and you get a new version of the JavaScript. What happens is when the index.html loads, sort of in the sort of beginning of that, there's a big hash that says, okay, for this file, here's the MD5 checksum. For this file, here's the MD5 checksum. So when the client-side code starts to run, it looks at all of those and it compares the MD5 to the MD5 we have stored in local storage. And if any of them have changed, it goes and retrieves that one file, but it doesn't actually retrieve the whole file. It retrieves a diff file, like a patch file. and it just applies the patch since we're all in text mode. So with this model, we literally are able to sort of, a change for our code, even a significant change for our code, to an end user when he's using the browser and sort of working with this is less than like maybe a K of change, which is great for us. We use Sass for CSS. How many people know what Sass is? Okay, Sass is, it's just a sort of higher level language of CSS. It gives you the ability to have variables and arguments and for loops inside your CSS files, and then it compiles that into CSS. The biggest benefit of that is, the benefit of any programming language, arguments and variables and loops, if-then statements, that type of stuff. You have Clojure for compiling. Clojure is just a JavaScript compiler. It does minification and compilation and removes dead code. We utilize Clojure heavily. If you actually look at Clojure really closely, it's a phenomenal compiler. It does more than just minification. It will look through your code and find dead code and remove it for you automatically. You can have it set up to remove your comments for you automatically so that when you do the compression, it doesn't include all the text from your comments, etc. It's actually really, really good at sort of outputting something that you can send to the user easily. So we talked about design initially, product design, that type of stuff. We've talked about code. We talked about the client side. We talked about the server side. So I'm going to go through the last two stages, which was test and deploy. And these I'll hopefully go through a little faster. And then what I was going to just do is a quick little demo on the iPad app that we just launched to give you an idea of like what's native, what's JavaScript, and like as we kind of play with it, you'll kind of see some of the nuances of the differences and stuff we're struggling with. So for test, for automation, on the server side, we use Vows to do automation testing. It's a Node-based module that does asynchronous testing. On Android, we use something called Robotium, which is very similar to Selenium, but for native Android apps. We use Selenium, obviously, on the mobile web. We use something called PhoneMonkey. So PhoneMonkey actually just has the phone app open. It can have it on a simulator, and it just randomly touches parts of the screen in random sequence, like a monkey. And it does that over and over and over, and we see how long it can last before the app crashes. And the goal is to just get the length that it runs to be longer. And if we can get that, I think what we found is if we can get PhoneMonkey, like there's threshold points. If you can get PhoneMonkey to last about 6 hours, that's like amazingly good because I don't know, there aren't that many people who are going to sit on the app and poke at it for 6 hours straight. So in general, PhoneMonkey actually finds a good number of crasher bugs very quickly. And then we use GHUnit, which is just a way to do unit-based testing on Android. We use Hudson for build management. So Hudson's just a building tool on every check-in. We use Git for source control system. For every check-in, we automatically have a build kicked off in Hudson, which then runs all of these different tests, and then either passes or fails the build. In terms, one of the big benefits, one of the big models that we use that's pretty big for us is the way that all of this stuff works and works successfully and doesn't grow out of scale is we do trunk-based development. So we literally have no branches. Everything's checked into master. All of the engineers check into master. And this is not just true for the mobile team. This is true for all of LinkedIn. So we check everything into master, and everything's built off of master, and everything's deployed off of master. We have an internal tool for layout testing. So it's actually pretty cool. We built a tool that will tap on the screen somewhere, take a screenshot, tap on the screen, take a screenshot, tap on the screen, take a screenshot. The next time you run it through, it'll compare the current screenshot against the previous screenshot and see if there's more than 5% pixel difference. If there is more than 5% pixel difference, then you know that the layout has changed. Sometimes that's because we changed the design and the layout has changed. And sometimes because we broke something. And it's a really good tool for us. We're probably going to open source this tool. We're working on that now. We use something called Phantom.js for performance monitoring. So Phantom.js is a headless WebKit browser. Headless means that it doesn't actually render UI anywhere, but it's a full WebKit-based browser. It has JavaScript. So the benefit is that you can run all of your client code that does DOM manipulation and everything inside it, and then you can sort of like send off little signals that say, hey, I just finished rendering this page. Oh, I just handled this click, that type of stuff. And then you sort of plot it out on a graph and kind of get an idea of where you are. We generally run bug bashes, and every 2 weeks we have demos. And I'll talk about in the deploy section how often we ship and how we sort of run stuff. So for deploying, we use enterprise builds that are available to employees. Enterprise builds, both Apple and Android. Android, I guess, you can distribute even if you didn't have an enterprise build. But Apple has this model of getting an enterprise certificate. If you get an enterprise certificate, you don't have to release your app into the App Store. Your enterprise can use it. Anybody who is inside your enterprise, so as long as it's on a corporate VPN, they can use it. We use this and let all of the people who work at LinkedIn get the latest version of the app all the time. We ship everything, all of the applications on the client side as well as the server side twice a week. So your natural question is, like, I don't see updates to the app show up every two days, so I don't believe you. So there's this embargo model that's available on iOS as well as Android where you can upload the app. They'll go through the certification, but then you get to decide when you want to release it. And so what we do is we just keep submitting. So we always have one that's available to be released. And then marketing and product sort of decide when is an optimal release time. And that's based on PR timelines, schedule timelines, that type of stuff. So it separates verification of the build and submission to the App Store from launch time. It gives us huge benefit because then we're not struggling at the last minute. The apps and the servers, they deploy independently because we have the screen-based JSON stuff. So that's version. The URLs are versioned. So because of a pretty good API, they deploy independently. We do 2-week bakes for really big stuff, right? Obviously, this model works really well when you're doing a whole bunch of incremental changes. If you're going to suddenly redo 2 or 3 screens in some significant way, we do a big bake. We use something called Keynote. It's a company for performance and availability monitoring from an external point of view. So we obviously do a lot of performance and availability monitoring inside LinkedIn, but we also like to have people poking at it from outside, like that are not associated with LinkedIn, because sometimes our tools lie to us. So Keynote does that. It actually has devices where it's polling the server as well as sort of like poking things and then gives us information. We use Device Anywhere and UTest for compatibility testing. So Device Anywhere has a plethora of Android devices, and we don't want to buy hundreds and thousands of different Android devices, and believe me, there's lots of variations. So you kind of give them a version of the build and say run it, and they give you back a report that says it worked on this device, didn't work on this device, crashes, that type of stuff. UTest we use, it's a crowdsourced testing model. So a lot of times, especially at the scale that LinkedIn is at, when you have millions of users, usually the tests we find when our testers run it are not the tests that our users find, or not the bugs that our users find. And so what we end up doing is we do crowdsourced testing. So we literally just give it out to a few thousand people, let them test it, and then get the response back. I talked about our internal monitoring stuff for QPS and uptime, and then we do crash log analysis. So whenever the app crashes, the next time it launches, at least for our employees and enterprise builds, not for consumers, we send up all the crash information and we try to track down the crashes. And that is about all the presentation side of it. I'm going to walk you through sort of a live demo on the iPad app a little bit. Okay, so let's start here. So this screen is actually So this screen here is actually is a native screen. The reason we did it native is to just effectively get this that little transition. Wow. So to get that to happen in the web was really kind of tough. So the rest of this screen here is all JavaScript based. The top title bar is native, but everything else is based in JavaScript and HTML. So even this is actually JavaScript and HTML using CSS3 animations. So there's nothing here that's native based at all. The crossfade that you see there is also in JavaScript and HTML. So everything in this app, we actually went a little bit further. We did actually, outside of that top little title bar and that, and this is, we call this the expose screen, and this expose screen, everything else in the app is actually web-based. So you can kind of get a feel. You can kind of get a feel for performance. It's, it's actually not bad. It can definitely be faster. I think that's something that we're going to focus on. But you can get an idea of like even the fades and even the sideways movements. All of this stuff is, you can kind of see it. Can you guys see this? There's like a slight chop to it. Maybe I'm the only one who notices this stuff. But there's a slight chop to it that is different from native. So even the load more and this type of stuff that's happening here, this is all happening inside iScroll. Pull to refresh, all of those aspects come from iScroll. So that's a quick little demo. You guys can obviously play with the app, and you'll see like slight. So like watch as I'm typing the letters if they're actually showing up at the right speed. You can see the sort of glitches in the way that the stuff sort of updates. Did you guys see that? I don't know. Just trying to point out the places where there's some slowness. But overall, the benefit that we get of doing this. So now you've seen it sort of run there. What I'm going to do now is actually go to tablet.linkedin.com. So now I'm running in the browser in Safari. Don't worry, I changed my password on purpose for this presentation. And you can kind of get a feel. So you can see the performance is the same in the browser as it is. And it's literally the same code running in both places. You notice that we do have this, so we still can generate this. It's just the transition is slightly different. It's a crossfade transition instead of going in and out. But everything else is fully running in the browser. It's 100% the same code. There's no sort of separation of a code base or anything like that. So, and the responsiveness is good. I mean, it's good enough that for most people it feels okay. And that's it. I'll take some questions if you guys have questions about the app or, oh, actually, there's one other thing I should probably show you guys before I. So one of the new features that we've added, and people ask me, oh, how did you do this? It's not native. But we did it, is this. So you can add your calendar. So this actually goes to the iPad's calendar. It sucks in the calendar information. And then shows you who you're going to be meeting with by looking up LinkedIn profiles. You're like, oh, this must be native. This is not native. This is also JavaScript-based. The way we did that is actually the web view. We've actually have like a little mini server running on the device. And the JavaScript makes regular REST-based calls to the native side to get the calendar data and then uploads it. So from all of the JavaScript's code's point of view, it's either talking to a remote server or it's talking to a local server, but it's just talking to a server. No sort of difference in the way that it works. So, and that bridge layer that we're creating and the wrapper for the web view, we're going to try to open source it so that other people can build access to capabilities like this.